part 1 is going to be calculating the head drop and flow rate in a single pipe segment. So to do that, we're going to start with an energy balance, which is going to be the change in pressure over the density plus acceleration due to gravity times delta Z, which is the change in heights, plus V2 squared minus V1 squared over 2, which will be equal to non-flower work over the mass minus the frictional heating. There's no non-flower work, so this will be 0, and there's no change in velocities, so this term will also be 0. We can go ahead and divide across by acceleration due to gravity, and we're going to get delta P over rho G plus delta Z is equal to negative frictional heating over acceleration due to gravity. This term is equal to our change in head, and frictional heating can be written as 4F, which F is the fanning friction factor, times the length of the pipe over the diameter of the pipe, times the velocity squared over 2, where the fanning friction factor, if the flow is laminar, is going to be equal to 16 over the Reynolds number, and the Reynolds number is equal to rho VD over mu, so it would be 16 over rho VD over mu, where mu is viscosity, and D is diameter, V is velocity, and rho is density. And if the flow is turbulent, then the fanning friction factor is found experimentally, and we will use the Churchill equation in our code. So now what we have is that delta head, which will represent as delta H, is equal to the negative 4 times F, which is the friction factor, L over D, length over diameter, times velocity squared over 2G. So the first step in coding this, we need to import numpy as np. That's going to allow us to use functions such as pi and log and whatnot. And we're going to go ahead and do from scipy dot optimize import Newton which is going to be used later to help us find the roots of our equation to help us find the flow. That's in part 2. So now to find the change in head, we need to use the Churchill equation to find the fanning friction factor, which can then be plugged into that equation that we solved for the delta head using the energy balance equation to find the change in head. So we need to start by making the function, and this is using the Churchill equation, and RE is going to be our Reynolds number, and ED is the relative roughness of our pipes. So this is just stuff that can be looked up. So A is going to be equal to 2.457 times np.log, which np comes from the numpy above that we imported so that we can have specific kinds of functions like log and pi and whatnot. So the log of 1 divided by 7 divided by the Reynolds number to the 0.9 plus 0.27 times our relative roughness of the pipe, all to the 16. And then B is going to be equal to 37,530. Oh, I box isn't on. All right, 37,530 divided by the Reynolds number. And we'll want to return the equation using A and B to get the fanning friction factor, which is going to be 2 times 8 divided by the Reynolds number to the 12th plus 1 divided by A plus B to the 1.5 to the 1/2. Oh, I'm sorry, that should be 1/12, not 1/2. And shift enter. And now our function is in there. So if I type F Churchill, shift enter, it should tell me that this is a function, which it does, because we defined this variable to be this function. So next we're going to define some variables that we're going to need. So first, acceleration due to gravity is going to be equal to 9.81. Pi is going to be equal to mp dot pi. We're going to say rho, or the density of our fluid, is going to be equal to 1,000, because we're going to assume that our fluid is water. And the viscosity of our fluid, because it's water, is going to be 1 times 10 to the -3. And our relative roughness is going to be 1 times e to the -3 as well. So we can shift enter that, and it'll put those in. I forgot an equal sign. All right, now it should work. And we can check our variables. So G shift enter should give us 9.81. And then we can do pi shift enter, 3.1415. And rho. All right, so these work. And now on to the next part. So now we need to define a function for our change in head. So we're going to start by doing that. So our change in head, which we're going to represent by d head, we're going to need Q, which is our flow rate, length of the pipe, the diameter of the pipe, and ED, which is the relative roughness of our pipe. From the energy balance, we found that the change in head is equal to -4 times the fanning friction factor times length of the pipe over the diameter times the velocity squared over 2 acceleration due to gravity. And so in order to define our function and to be able to calculate the change in head, we need to calculate the velocity. We know that the flow rate is equal to velocity times area. So using that, we can find that velocity is equal to the flow rate divided by the area of our pipe. So Q divided by A, where A is going to be equal to pi times the diameter of the pipe squared divided by 4. So in order to calculate the change in head, we need to know the fanning friction factor, which we solved using the Churchill equation up here. But notice how it requires the Reynolds number. So what we need to do is down here to define and write an equation for the Reynolds number. So Reynolds number is equal to the density of our fluid, so rho, times the velocity, times the diameter of our pipe, divided by the viscosity of our fluid, mu. Now what we want to do is return that value for the change in head. So to do that, we'll type return, and we need to plug in the equation for the change in head that we solved for in our energy balance using the Churchill equation to find the fanning friction factor, the velocity, and the Reynolds number. So return 4 times F, that should be lowercase, F Churchill, and we need to put RE, and which is the Reynolds number, and ED, which is the relative roughness of our pipe, times the length of our pipe divided by the diameter. We're going to put these in parentheses, and that's times the velocity squared divided by 2 divided by acceleration due to gravity. So for our change in head equation to be more realistic, we're going to incorporate a K constant, or a K value. So it'll be K plus then the rest of our equation. So that K is a value that factors in if there are any 90-degree elbows, contractions, or anything else within our pipe. If there are multiple, then we would end up adding multiple K values. So we know that we can get a negative flow rate, and that means that that's just related to the directionality of our flow. So it was going in a direction opposite of what we thought. So if we thought it was from 1 to 2, really it's going from node 2 to node 1. But that negative sign indicating the direction can affect equations later on, such as square roots and logs. So we want to take the absolute value of that so that our velocity is a positive number. So mp dot absolute, and that should make this an absolute value. So we'll go ahead and shift enter. And since we took the absolute value to get rid of the sign, we need to factor it back in. And so we'll put that here at the return. So negative mp dot sign of our flow rate, which is Q, in parentheses. We need to multiply these together. Now shift enter. So now we're going to define the function for our flow. So define flow, and we're going to use delta head for that. There we go. Nope, there we go. The length of our pipe we'll also need. We'll need that K value, which factors in any elbows or contractions. We'll also need the diameter of our pipe and the relative roughness of our pipe. So we know that our flow is equal to velocity times area, where area is going to be pi times the diameter squared. Divided by 4. And we know our velocity is using the delta head equation to solve for velocity is going to be the square root of the negative delta head times 2 times the acceleration due to gravity divided by K plus 4 times the fanning friction factor multiplied by the length of our pipe divided by the diameter. So we can go ahead and subtract that, or delete that part, and we're going to put this in parentheses and multiply the area by the velocity using the equation that we got from the energy balance and solving for velocity instead of the delta head. So that's going to be mp.sqrt, which takes the square root of the delta head. There we go. times 2 times acceleration due to gravity divided by, and we're going to put this in parentheses, the K factor plus 4 times our fanning friction factor, which we're just going to put little f right now. We're going to go back and change that in just a second because we haven't defined that variable at all. And then we need to multiply that by the length over the diameter. So in this part here, we're trying to find the change in head when we know the flow rate. So because we know the flow rate, we can find the velocity, which in turn gives us the Reynolds number. And that is used to find the change in head using also the Churchill equation. But down here, we're basically doing the opposite. So in this case, we know the change in head and we're trying to find the flow rate with that change in head. But to get the flow rate, we have to make a guess because we need to know the velocity. We need to make a guess for the flow rate. And we'll use a root finder to find that flow rate where the delta head that is calculated for this guess that we're about to make is equal to the head up here that is supplied. So this Q, which is our flow rate, we're gonna say is Q guess, because this is our guessed flow rate. And instead of F right here, which is the fanning friction factor, we're gonna put 0.01, because when you look at a graph of the fanning friction factor, a good guess for that is 0.01. So then we're going to go ahead and shift enter that. So looking back at this equation for our flow rate guess, we see that we're taking the square root of a value. Well, because of the delta head, this value can be negative. So what we need to do is have the absolute value of our delta head. So we're going to go ahead and make another variable called ABS, which is absolute, and delta head, which is going to be equal to MP dot absolute, or ABS, which is the absolute value of our delta head. So in here, what we are going to now put is ABS underscore delta head to get our absolute value there, so that when we take the square root, there isn't a possible negative sign underneath the square root, which would cause errors in our code. So we need this flow rate guess in order to find the Reynolds number, because the Reynolds number is dependent upon knowing the velocity. And in order to find velocity, we see up here that we need to know the flow rate. So we're going to start with a guessed flow rate to where the flow, we will then have to use a root finder. So that's what we put in here, up here. We imported a Newton root finder for a later part so that we can find the flow rate where the delta head that's calculated here is equal to the change in head that is supplied. So to do that, we need to define another function. So our flow to 0. So what this is going to do with our flow in there, Q, our flow rate, this is going to help return the value so that the delta head up here with the arguments that are inside it, so Q, L, oh, I forgot to include K, right? Q, L, K, D, yes, okay. I forgot to include Q, which is the part that we added right here to make our equation more realistic, to factor in 90-degree elbows and contractions and other types of changes in the pipes. So we know our flow, our length of the pipe, K, the diameter of our pipe, and the relative roughness of our pipe. I did not need the colon. And then minus the delta head, that is here. So we're going to find the flow that gets us to where the calculated head minus the supplied head is equal to 0. So now I have this function, and this is the function that we want to zero out. So when the calculated change in head is equal to the supplied change in head. So to do that, we're going to use Newton's method, which is why earlier we put in from scipy to optimize import Newton root. That's going to import the needed function that we are going to use to find the roots of this equation. So our result is going to be equal to Newton. And now in this first part, we need to put the function that we want to, the function whose zeros we want to find. So that's going to be f to 0. And we need to put in an initial guess. And so that's why we now have q guess. So that's, we're going to go ahead and put that in there. So q guess. Close the parentheses. And so we want to return the result. And so we'll type return res to get that result returned. So we've already looked at a couple of pitfalls that could have occurred in our code, such as taking the absolute value of the formula used to calculate velocity, since if our velocity is negative, it could result in a negative Reynolds number, which doesn't work with our Churchill equation, because when you look at a graph, there aren't any negative Reynolds numbers. And then the other pitfall that we've discussed so far is incorporating the sign of our flow rate in here, because when you calculate Q and we get our velocity, we end up plugging our velocity into this equation, but we square it. So if it's a negative velocity or a positive velocity, because it's squared, we're going to end up getting the same answer. So what we ended up incorporating the sign of our flow to account for if this was a negative velocity, so that we get the differences between a negative and positive velocity for the delta head. So then the next pitfall that we need to look at is, what if our change in head was 0? So the next thing we need to look at or account for is if our delta head, or the absolute value of our delta head, was really, really small or equal to 0. If it was equal to 0, then when using the root finder, we would get a lot of errors. So in order to avoid that, what we're going to do is incorporate an if statement. So if the absolute value of the delta head is less than, we'll say some really, really small number, so 0.0000, oh, we can write this in an easier way, 1 times e to the -10. If it's less than that, what we want it to do is return the value as 0.0. So if the flow is equal to 0, or a really, really small value, or I'm sorry, not the flow, if the change in head is 0 or some very, very small number, it's going to return that the flow is 0. So we're going to go ahead and shift enter that. There shouldn't be spaces here. Delta head is less than. That is the right syntax. I forgot colon. There we go. Now it should work. There we go, and we don't get an error. So because we have that square root here and we had to take the absolute value of the delta head, We're doing all the calculations assuming that value is positive to avoid any errors, but since our delta head can be negative, what we need to do is multiply our final result by the sign of delta head in case it is negative. So NP dot sign of delta head times the result is going to give us the sign multiplied by our result to factor in, if in case it was negative, to factor that negative back in. So shift enter. So now what we have is a formula in order to find our change in head and a way to find our flow. And we have talked about any possible pitfalls and have accounted for any negatives or anything that could affect our equations, or really small numbers, or if the delta head's equal to 0. And that completes part 1 of exam 2.